Welcome to this explainer, brought to you by Academic Zenith Online Academy. Today, we're doing things a little bit differently. We are going to treat chemistry exactly like a video game, and I'm here to give you the ultimate cheat codes for balancing chemical equations. Seriously, if you've ever stared at a messy jumble of letters and numbers in chemistry class and felt completely lost, you are absolutely in the right place. So, grab your controller, let's dive right in and level up your chemistry game.
Okay, so to play any game successfully, you first have to understand the core programming, right? The unbreakable rules of the universe. Well, in chemistry, our universe is governed by the law of conservation of mass. As Antoine Lavoisier brilliantly established way back in 1789, matter is neither created nor destroyed. What this actually means for our game is that every single atom that enters into a chemical reaction on the reactant side, well, it has to wind up somewhere in the products. They don't just magically disappear, they just change places. You have to finish with exactly what you started with.
So, game rule number 1, coefficients versus subscripts. Before we just start mashing buttons, let's look at what we're actually allowed to change. Here is the golden rule, the one thing you have to remember. You are completely allowed to adjust the coefficients, those big numbers you place in front of a chemical formula. Changing a coefficient just changes the quantity of that specific molecule. Easy enough, right? But you can never, ever touch those tiny little subscripts. Subscripts define the actual identity of the substance itself. Like if you change the subscript in H2O to H2O2 just to try and balance an equation, you've literally just turned life-giving drinking water into toxic hydrogen peroxide. And that is a quick game over. So, this rule is completely non-negotiable. Do not change subscripts. Coefficients are your only tool here. Oh, and here's another great tip. Polyatomic ions, those little groups of atoms that stick together, they usually stay totally intact throughout the whole reaction, so you can actually balance them as a single group rather than picking apart individual atoms.
All right, if you just guess and check, you're going to run out of lives fast. Let's unlock the ultimate cheat code, the Mino method.
There's this fantastic, kind of goofy mnemonic to help you remember this one. "Me no chemistry," said Tarzan as he climbed the stoichiometry. It's silly, but MINO tells you the exact optimal order you should balance your atoms so you don't mess up your previous steps. First, you balance your metals. Then, your polyatomic ions. Next, your nonmetals. Then oxygen, and finally hydrogen.
A massive piece of advice here. With combustion reactions especially, it is so much easier to leave oxygen for the absolute end. Because oxygen and hydrogen love to spread out across multiple compounds in reaction, saving them for the final steps of your Mino method stops you from having to constantly redo your work. Seriously, it is a huge time saver.
All right, player, let's put it to the test. Welcome to level 1, synthesizing water. We're starting with our unbalanced skeleton equation. We've got hydrogen gas, H2, reacting with oxygen gas, O2, to form water, H2O. It's a completely valid reaction, but if you look closely, it's breaking Lavoisier's law. The atoms are unequal on each side of the arrow. Let's pull up our scoreboard. On the reactant side, we have 2 hydrogens, and on the product side, we have 2. Okay, so far so good. Hydrogen is tied. But looking at oxygen, we have 2 on the left and only 1 on the right. We're literally missing an oxygen atom. And remember our golden rule, we can't just slap a tiny subscript 2 onto the water molecule, we have to use coefficients.
So, to fix the oxygen, we put a coefficient of 2 in front of the entire H2O molecule. Boom! That gives us the 2 oxygens we need on the right. But wait, hold on. That coefficient multiplies times everything in the molecule. Now we have 2 times 2, which is 4 hydrogens on the product side, while we still only have 2 on the reactant side. Our hydrogens suddenly got knocked out of balance.
Don't panic, this is just part of the trial and error gameplay. We simply hop back over to the reactant side by placing a coefficient of 2 in front of the H2 reactant. We bring our hydrogen count right back up to 4. Let's check the final board. 4 hydrogens on the left, 4 on the right. 2 oxygens on the left, 2 on the right. We have reached a perfect balance using the lowest whole number ratio. Level 1 is officially complete.
Ready to crank up the difficulty? Let's jump to Level 2, the combustion boss battle. Here we have methane, CH4, reacting with oxygen, O2, to yield carbon dioxide, CO2, and water. Now, if we just start balancing randomly, we'll be here all day. But per the Minosh rules, we don't have metals or ions, so we look at nonmetals. We have to balance our carbon first, deliberately leaving our oxygen and hydrogen for the very end. Checking our starting scoreboard.
Carbon is actually already balanced, one on each side. But look at the rest of this mess. 4 hydrogens on the left versus 2 on the right, and 2 oxygens on the left versus a total of 3 on the right, because the oxygen is split between the carbon dioxide and the water. Our numbers are just completely mismatched here.
So following my no, we tackle hydrogen next. We have 4 on the left, so we absolutely need 4 on the right. We add a coefficient of 2 in front of the H2O. Awesome, that successfully gives us 4 hydrogens. But remember, it also changes our oxygen count. We now have 2 oxygens from the CO2, plus 2 oxygens from our new water molecules. That bumps our total product oxygen up to 4.
All right, final move. We need 4 oxygens on the reactant side to match the products. Since oxygen naturally comes as O2, we just pop a coefficient of 2 right in front of the reactant oxygen. 2 times 2 is 4. Let's verify our work. 1 carbon, 4 hydrogens, 4 oxygens on both sides. We have balanced the equation perfectly with the lowest whole number ratio. You just beat the combustion boss.
Balancing equations isn't just a fun puzzle to beat. Let's talk about why this actually matters in the real world.
Because out there in a real laboratory or, a massive industrial manufacturing setting, an unbalanced equation is basically a recipe for disaster. It leads to entirely incorrect ratios of your chemical ingredients, and that means failed experiments, unpredictable reactions, lost time, and a massive waste of really expensive resources. Proper balancing is literally the only way to ensure that your theoretical, on-paper yields actually match your real-world physical results.
So please keep this critical definition in mind. These coefficients, they're not just arbitrary numbers we throw around. They are the exact mathematical tools that let us respect Lavoisier's incontestable rule. Think of them as the scale weights that keep the whole universe of your chemical reaction in perfect harmony.
Now that you know the rules, you understand the cheat codes, and you see exactly why this all matters, I'm going to leave you with one final real-world challenge. This is an infamous final boss equation, taken straight from our sources. It is a completely real reaction, and some say it can literally take up to 2 hours to solve if you don't use your strategies properly. So write it down, apply the MINO method. Are you up for the challenge? Good luck, keep leveling up, and thanks for joining this explainer from Academic Zenith Online Academy.